Thanks everyone for coming. Today's speaker is Huanyu Zhang. Huanyu is a graduate student in Cornell, and this summer he interned in our group. He worked on some cool projects on differential privacy, but today he's going to talk about some of his other work on privacy preserving statistical learning and testing. Huanyu.
Okay, hello everyone. So thanks, Jenna. So today I'm very glad to give a talk here, and my topic is on privacy, preserving statistical learning and testing. Okay, so first I will talk about some introduction and motivation, why we need private statistical learning and testing, and the second section and the third section is main technical part. So the first problem is on the differentially private identity testing, and the second problem is on the differentially private property estimation. And at last, I will also mention some future works. Okay, so let's start with the introduction and the motivation. So there are some old and classical statistical learning and testing problems. The first problem and maybe most famous one is distribution learning. For example, you have some coin, and you want to estimate the bias of a coin. Okay, just a learning problem. And another famous problem is some hypothesis testing problem. For example, you have a coin, you just want to test whether the coin is a fair or not. Here, fair just means it will show up tail and head with the same half probability. And last, there are also some problem named property estimation. Suppose you are given some IID samples from some unknown distribution. You want to estimate the property of this distribution. For example, you want to estimate the Shannon entropy of it. Okay, so these are old and also well-studied problems, but the problem is that the previous studies mainly focus on the small domain setting. Here, the small domain setting means it has a very small alpha byte size, and you have many more samples compared with the number of the alpha byte size. For example, in the example of a coin, the alpha byte size is only 2. But for now, we want to look at some other settings. As everyone knows, we are in the era of big data, so we have lots of many data and bytes of data generated every day. And the big data has brought huge success for machine learning and statistics, but also some new challenges. So what is the new challenges? So now we are not focusing on the small domain setting, but we want to focus on some large domain setting. Here, large domain setting, the reason is that because we will need to estimate or test a lot of distributions over large domains or high dimensions. For example, if we want to deal with some gene mutations, which has a really huge sample size, okay? And also another reason is that the data is quite expensive. So we want to use as small number of data as possible. So today, we will focus more on the finite sample setting, which means we will mainly focus on the sample complexity, which is defined as the minimum number of samples we need to do some task. Okay? And also, we also need to consider some constraint of privacy. So, the reason it should be obvious, because the samples may contain sensitive information. We just want to do the same testing or learning problem, but we also want to preserve the privacy for the individuals who contribute data to us. Okay? And also some more examples on why we want to, on the private data, because data may contain sensitive information. For example, in medical studies, because, for example, if we want to learn the behavior of genetic mutations, which contains health records or disease history. Okay, this is one example that data contains sensitive information. And also in some other application, like navigation, because in navigation, who suggests the routes based on aggregate positions of individuals, because the position information can contain a lot of sensitive information, and it can indicate user residence. For example, if Google Map finds me always at Microsoft, maybe he will find me, I should be a staff of Microsoft, right? So, which means here the data is kind of contains sensitive information. Okay, so what we want to do is to do some private inference. Okay, so what we want to do is just want to do the old problem, also with the constraint of the privacy. And furthermore, we want to explore the privacy sample complexity trade-off in these problems. And usually, and which we will find later, So the sample complexity of these problems can be divided into two parts. The first part is just the sample complexity of non-private algorithm. And the second part is just additional cost due to privacy. And then a natural problem, an interesting problem is that is privacy costs a lot or very small or even free. So why is it important? Because when the privacy cost is very small, we can just incur the constraint of privacy with very small cost. Okay, so now we need some notation of the privacy. Here, the notation for privacy we use is the differential privacy, which should be the most famous one notation for the privacy. I think everyone should be quite familiar with it, but I just want to briefly go over it. The definition is that when you change one sample in a data set, the output distribution won't change a lot. If we look at the plot, the graph here, so we have two data sets, D1 and D2. They only differ at one position. For example, so I just changed x1 into x1 prime. So they only differ at one positions. And f hat is some randomized algorithm which you need to design by yourself. So the differential privacy just requires that the distribution of the f hat on the condition of the first data set and the distribution of f hat on the condition of the second data set should be close. Here, close is some multiplicity ratio can be bounded by some e raised to epsilon. And we can find that when epsilon is really large, you will have a very weak privacy constraint. For example, if you take epsilon to be infinity, you have no constraint of it. And if when you take epsilon to be 0, you will have a very stringent privacy constraint, which means that you need the distribution to be almost the same. Okay, so DP is widely used by the industry, for example, Microsoft and Google. Okay, so
what is the distribution here? So what is random distribution and function?
Okay, so the randomness comes from your algorithm. So the f hat is your algorithm. So the data
is random.
Yes.
Then what is the distribution here? Is it a fixed vector or a distribution?
It should be depend on your data set, right? When your data set is fixed, and you will also have some distribution because your algorithm is random.
Yeah,
the distribution is over the range of the output of the algorithm.
Right.
Oh, in that sense, not in terms of the inputs.
Yeah, in particular, the inputs can be, the input X or whatever is fixed, like you assume anyone.
Just checking.
Okay.
Yes.
Worst case privacy.
Yes. Mm-hmm. And you can find that you must use some randomized algorithm, right? If you use some, if you don't use randomized algorithm, you cannot have this guarantee because the distribution will be kind of fixed. Okay, so now, I just want to talk about one framework to change non-private algorithm to private algorithm. Okay, and which is the Laplace mechanism, which is the most famous one. So I need to define sensitivity at first. So the sensitivity of a non-private estimator f is defined as when you change one data set, when you change one point in the data set, the maximum possible change for the output. This is for the non-private estimator because I'm talking about changing a non-private estimator to some private estimator. And you can imagine that if sensitivity is large, which means that for the non-private estimator, when you change a point, it will change a lot in the output. Okay? So now, what is the famous Laplace mechanism? It can be divided into two steps. The first step is that you design a non-private estimator with low sensitivity. And the second step is just you privatize this estimator by just adding some Laplace noise. And you can see here is the Laplace noise with standard deviation of the sensitivity divided by epsilon. And you can find that when the sensitivity is very large, which means your non-private estimator is quite bad, you need to add a lot of noise to make it differentially private. Okay, and the epsilon just the privacy parameter. When epsilon is small, you have a higher requirement for the privacy, so you need to add some more noise of it. Mm-hmm. Okay, so now this talk we will contain the following two works. The first work is on differentially private testing, identity testing, and colonies testing, and which is done by myself and Jayadav, which is who is my advisor, Ziheng, who is my lab mate, and also another work is on the differentially private estimate some property estimation problem, and this is joint work with Gaussian. Okay, so any problem till now? So I just want to start the technical part. Okay, so the first one should be the differentially private identity testing. Okay, there is one motivating example for the identity testing. So which is a famous and is a true story. Is a Polish lottery named Multilotic. Okay, so and it said that this lottery is fair by choosing uniformly at random distinct 20 numbers out of 1 to 80. Okay, so now the problem we consider is that is the lottery fair or not? Here, fairness means every number comes out with the same probability. Okay, so and the answer for this problem is no. So because if you draw the histogram of the 300 drawings of this Polish multilotic, you will find that the number 50 to 60 is very small. So you will, with high probability, you can see that this one should not be a uniform distribution, right? So this is because the machine is biased. There is something wrong with the machines. Okay, so the idea is that we just want to see whether some distribution is same with our known distribution or not. Now we just formalize it by this problem formulation. So this problem is very famous, named as identity testing, also goodness of fit. Someone also named as one sample testing. So we will see the two sample testing later. So we only care about the discrete distribution. We see the support size to be k. K just 0, 1 into k minus 1. And we suppose Q to be some known distribution. Okay? Some known discrete distribution over k. Now what is the task? The task is that given xn different independent samples from unknown p, x1 into xn, we want to answer the following question: whether p equals q or not. Okay, so what is the definition of our tester? Our tester should be just a function from the random samples into 0 and 1, which should satisfy the following things. With high probability, our tester should output 1 if p equals q. Okay, you can see the tester is kind of a classifier. You just need to justify whether p and q are same or they are alpha away in total variation distance. Maybe you will ask me what will happen if neither of the condition will satisfy. So the answer is we don't care. So you can let your tester to output either 1 or 0 with no guarantee. Is the problem clear? Okay, so and we mainly concern about the sample complexity of this problem, which is the smallest number of samples where such a tester exists. And you can find that the sample complexity should depend on this Q unknown distribution, right? Suppose you have some one spike known distribution. You can see it should be independent of the support size. Okay, so here the sample complexity is defined as the worst case. Here the worst case means the worst among all the Qs. All the Q is some known distribution on the support size K. Any problem for the problem definition? Okay, so there are some previous results. So for the non-private problems, so the known sample complexity for this problem is square root k divided by alpha square, which is shown by Pansky. This is tight. Okay, so which means you don't need a linear number of you don't need a linear number of samples. Here, linear means the linear in alpha by size. You only need some square root k dependency of it. And I can give you some lower bound intuition, which is just a birthday paradox. Okay, so because we don't have enough people here, so I don't think I can make a real experiment. But the birthday paradox is that, yes, suppose you have a uniform distribution on a support size k. So, and you just IID draw some samples from this distribution. Okay, so and only if when you have some square root k number of samples, you can see some collision. The collision means you will see let's say two samples which belong to the same symbols, something like this one. And for these problems, we can just show a very easy argument to prove a square root k divided by alpha, square root k lower bound for this problem by this birthday paradox. You can just assume you have two distributions. The first distribution is uniform on k, okay? And the second distribution is you have uniform on k over 2, but you don't know what is the support of this k over 2, okay? So now you just want to distinguish between these two, okay? So what you can do, just randomly draw some samples. And if you draw some samples which is less than square root k, the claim is that for these two cases, you will see the samples are almost the same. Because you cannot see the collision, right? Because you will see, okay, every sample appears with, every symbol will only have at most one sample. So for these two cases, the samples look exactly the same. So you cannot distinguish between these two. So which gives you a lower bound of square root k something. Okay? So and this is for the non-private case. And for the epsilon differentially private algorithms, in the paper of Tsai and also Gaussham's paper, so they show an upper bound of square root k divided by alpha square plus square root k log k divided by something. And you can find that this one is just a cost of the non-private estimator, right? And this term, it should be the cost because of you incurring the constraint of differential privacy. Okay? So what is the problem for this estimator? Because this estimator is based on a chi-square test, which has a very high sensitivity. Okay, so what did we do? We just show that for this problem, we have a tight bound of square root k divided by alpha square plus the maximum of these three items, and we show it's tight. Here, tight is for all the parameter ranges of k, alpha, and epsilon. Okay?
Wait, what did you say from the previous thing? Can you go back?
Which one?
Oh, I see. There is this log k term here. That's what you're saying.
And even if you get rid of
And
the
also-
log k term, there's still like worsen the exponents in the denominator.
Right.
Alpha to the power of 3 halves. But alpha square dominates, no?
Depends on the value of
Okay.
epsilon.
And always we are considering the large k case. So we have a very huge upper byte size. You can see k is very large.
Okay, yeah. Just
Yeah.
wanted to see what's there.
Yeah. So what we show is that, okay, we can just show more. So when epsilon to be infinite,
Wait, epsilon is privacy.
epsilon is privacy. Alpha is some accuracy level. So alpha is defined here.
Yeah, I got it. But
Yeah. And epsilon is for the differential privacy parameters. Okay. So what we show is that when epsilon goes to infinity, which means you have no constraint on the privacy, right? You will see these three items will be 0. So you will only have the first item, which is square root k divided by alpha square, which is the cost for the non-private estimators. Okay? And also when k is large, what we have is square root k divided by alpha square root epsilon, which is strictly better than the previous result. Okay?
yeah, just when epsilon is privacy, saying epsilon tends to infinity seems a weird statement to me, but I get what you want to say.
Yeah, I just want to see this one can be modified.
Yeah, it's in limit. Yeah. Okay.
Yeah, it can be.
Well, why does it seem weird? I mean, it's just saying that like if you don't have a privacy constraint. if
Yeah,
epsilon-
but then why should I use this algorithm? Like even the previous algorithm will also occur square root k, right? The
Sure.
trivial one.
Sure.
Yes.
Yeah, I mean it's fine. Mathematically it's fine, but it just seems weird when you say epsilon, you take it to infinity.
I see.
You're studying a privacy problem. That's
Okay. Okay, so what is our contribution? So we have new algorithms for achieving better upper bounds, and we also have new methodology to prove lower bounds for this kind of problems. I need to point out the more interesting part should be the lower bound, to how to prove this is optimal, so for all the parameter ranges. Something like that. And okay, so the first argument I want to make is, I just want to talk about some reduction from identity testing to uniformity testing. So what does it mean? It just means that if you have some, okay, let me define uniformity testing first. So the identity testing when Q is a uniform distribution over K. So the known distribution is just a uniform distribution over alpha byte size. Okay, so my claim is that if you can solve the uniformity testing, okay, it's not my claim, it's the previous works. In the non-private case, up to constant factors, if you don't care about constant factors, if you can solve the uniformity testing problem, you can also solve the identity testing problems. You will only with the cost of some constant factors. And also we know uniformity testing should belong to the identity testing, right? Because uniform distribution is just one special discrete distribution on the support set K. So because we only care about the worst case guarantee, so we can argue that the sample complexity for these two will be the same, up to constant factors. Okay? And what we show is that this one is also true for the private case. So anyone interested in how to do the reduction? Okay, so suppose now, okay, what is the reduction? Suppose you have some uniformity testing algorithm. You want to solve some identity testing problem, right? Okay, the reduction is something like you can find a mapping from the known distribution to the uniform distribution. And you can also map the samples in some ways. And you can show that if you have Q, which is a known distribution, and someone alpha away from Q, you will also have some uniform distribution and someone 6 alpha away from uniform distribution, something like this one.
So it's generally true for any distribution.
Yes.
In any dimension.
Right.
Okay.
So if you want to, I can also point out a special case. It's just if you want to see some lattice-like distribution, which means that every mass can be seen as, what do we see? So I would like to see, so for the, for any I, Pi equals something like AI multiply T. T is just some mass, so you can see that as so which means for every distribution, it can be seen as the one integer times the mass of here. You can have something here. So what should be the right mapping? You can just map this one to be the same on the uniform distribution. This is 2 times of it. You just map it by something like 2 in the large domain size. And this one is 3, you just map it into some 3 somethings. And
Then don't you need to increase the domain size?
yes, of course. So you can show that. So this one, yes, you will increase the domain size from K into 6K, some constant number of K.
Constant suffices?
Yes.
But what if one is small, one is huge? Like one bar is small and one bar is huge.
But this one is okay. Okay, so this is only the special case of the lattice, but they also show the general mapping from the. So we're not in lattice case. Okay. Yes, I see. That's the intuition for the lattice. Okay. So now what I want to see. Okay, so now it would be sufficient only to consider uniformity testing, right? Because we show the sample complexity is the same, up to constant number of factors. Okay, so now we just come to the algorithms. So we just see the binary case first. Okay, now here the binary case is that we only have alpha set to be 2, which is just a binary distribution. Okay, so we just want to distinguish between Bernoulli half and Bernoulli B. And we just want to test whether B is 0.5 or alpha away from each other. What you should do for the non-private case? So you can just randomly draw n samples and let M1 to be a number of ones in the samples. And you can imagine that if you draw just from Bernoulli half, the M1 should be roughly n over 2, something like, right? And if you draw something is alpha away from 0.5, you will have something like n over 2 plus alpha n something, right? So what should be the right algorithm for it? You can just have some hard threshold algorithm. So for example, and this is the PDF, and this is the number of ones. So if it's exactly from Bernoulli half, it should be a binomial distribution with the expectation exactly 1/2 multiply n something, right? And if it's not from the Bernoulli half, it should be another binomial distribution, just from 1/2 plus alpha multiply n something, right? And you can imagine that when n is getting larger and larger because of the concentration, this one and both these two will have a smaller variance when n is bigger and bigger. So when the standard deviation is smaller than the expectation gap, and you can distinguish between these two. This is a rough idea for the non-private case. So what should be your algorithm? Your algorithm should be something like for here, you just output. If the number of ones is smaller than something like 1/2 plus alpha/2n, you just output. Here is there should be the probability to output different. So I just want to, this is the probability to, or suppose you have some randomized algorithm, okay? So, and this y-axis is just a probability to output, they are different. Okay, so what should be your algorithm? You just have 0 here. And before this threshold, you have 0 probability to output, they are different. And here you just have a jumping. Here you have 1. And when it's larger than some 1/2 plus alpha/2, you will just output, okay, these two are not the same. This is the case for the non-private case. So, and the analysis is very simple. It's just when n is large enough, the standard deviation will be smaller than the expectation gap, and which will give you a bound of 1/alpha squared something. This is a non-private. Okay, so what will happen in the private? So because of the because of the differential privacy, what does it mean? It means that when you change one sample, you cannot let your output probability to change a lot. So you cannot have some hard threshold algorithm like this one. Okay, so what should you do? You should just you just want to smooth it by some sigmoid functions. So it's just kind of like some ideal filter and some real filters. So in a non-private case, you will have some ideal filters. You just have a huge jump and you lose nothing. But in this differentially private case, because you require, you are not allowed to have a huge jump in the output of the distribution. So what you do is that you just use a sigmoid function to smooth it. Any question here? So the algorithm is named some soft threshold, which is just something like, okay, Z is the difference between the M1 the difference between M1 and N/2. So we just also see something similar here. And so beforehand, we don't have some sigmoid function. We just have, okay, if this one is smaller than 0 something, we just output the same. I also will output different. But now we just smooth the probability by some sigmoid function. Okay? So, right. Okay. So, and this is the analysis of it, but it's not quite important. So we need to prove it in 2 aspects. The first aspect is on privacy. Okay, the privacy guarantee is not hard just by the property of sigmoid function. Because we know the sensitivity for the M1 is just 1, right? So when you change one sample, the M1 will at most change 2, change some constant. Okay, so what will happen? This one will change at most 2. So the gamma here is something like 2 epsilon. So you will have e raised to minus epsilon, and between e raised to minus epsilon and e raised to epsilon, which is just a requirement for the differential privacy. And also for the utility analysis, it's also not hard. So you don't need to read this one. It's a kind of messy. So the intuition is that suppose we consider the real distribution is Bernoulli half. Okay? In that case, M1xn, which is the number of ones in the samples, should be roughly n over 2. Not true? Suppose the number of samples is large enough. So the things in the Pearson's is roughly minus O minus alpha n, right? So what we need is that we need the epsilon multiply alpha n to be some constant, because we need to have some huge constant for the sigmoid function. So we will have some guarantee like alpha n epsilon to be 1, so n to be have a bound of 1 over alpha epsilon, something here. Any problem till now?
So this privacy is in central model.
It's a central model, global. But there are also, for the same problem, there are some
So
IoT.
is it obvious that the algorithm without differential privacy is not already DP?
Yes, I think so.
Why?
Because you can just so it's not a randomized, even not a randomized algorithm, right?
Yeah,
So
but it is in terms of n, right?
but how could a non-randomized algorithm to be DP? So suppose you fix the data set, the result of the algorithm is fixed, right? And we just argue that the non-randomized algorithm cannot be differential privacy.
Okay. Yeah, but it intuitively feels like if they are also doing some sort of like empirical average kind of a thing, it shouldn't change much, right?
Yes. So what we do is just go to check what is a low sensitivity non-private estimator, and we just do this kind of sigmoid trick to make it private, something like this. Okay. So what we next
So
step
is
should
that sigma trick just doing exponential function?
yes, you can even do a Laplace here. You can even do a Laplace noise, but using sigmoid function seems more fancy. So, but you can use Laplace mechanism here, and exactly the same. Because the sensitivity is very small for the M1 xn, it's just 1 something. Yeah. Okay. So now we come to the general case. So the idea is we just want to privatize the statistic used by the previous papers. So let Mx be the number of samples. So this is the non-private estimator they use, which is just an empirical L1 total, not L1, empirical total distance between the empirical distribution and the uniform distribution. So this one has the following 2 properties. The first one is the sample optimal in the non-private case. And the second property is the statistic also has a very small sensitivity. So what we do is, and they also have some property on the expectation gap and the small sensitivity. So they show in their paper that the expectation gap of this one can be bounded by the following 3 terms. And also, you can see they also have some 3 terms, so which match the bounds for our results, the 3 different items in our bounds. And also, it's very easy to prove they have a very small sensitivity, only in the minimum of 1 over n and 1 over k, where n is the number of samples and k is the alphabet size, depend on what is the value of n and k. Okay, so what we do to have this algorithm is the idea is very simple. So what we do is that we do almost the same kind of trick with the Bernoulli case. Okay, we have something, we just minus some gap here, and we smooth it by using some sigmoid function. And using exactly the same analysis, we can get the bound corresponding to our main theorems. Okay, so you can see that you just need something like this one multiply k multiply epsilon to be smaller than some constant, something like this one, and you will get the bound. Okay, so any problem till now for the upper bounds?
I have a question. I don't have a problem, but so is this actually the right way to like add noise. Do you guys show that this is also sort of like the optimal level?
Yeah, we show this matches the lower bound for these problems.
Actually, that's interesting.
Yeah. Okay, so now comes to the lower bound argument. Okay, which is I think is more interesting. So we have the following lemma. Suppose there is a coupling between P and Q over Xn. So I just want to point out Xn is not necessarily IID. So such that the Hamming distance between Xn and Yn is small. It can be bounded by D, and we show that any epsilon dp algorithm which can distinguish between these two can be bounded at epsilon will satisfy epsilon to be omega 1 over D, something. So what does it mean? If you want to prove some lower bound, you need to find some coupling between P and Q which has a very small expected coupling distance. Okay, so for example, if you have the naive bound for D should be infinity, right? So in that case, you will have epsilon is greater equal than 0, which is nonsense. So you just want to find find some distribution with as small expected Hamming distance as possible. Just rough idea. Okay, so lower bound we have also. First, we see a lower bound for the binary case. Okay, so for any distribution P1 and P2 over X with total variation alpha, so if we draw NIID samples, there must exist coupling with expected Hamming distance alpha n, which is the most famous maximal coupling argument, right? Because total variation, okay, for IID case, if you look at one sample, the total variation is a probability they two are different. And now you have n, so you will have some expected Hamming distance of n alpha, something like this one, right? And just by this argument, if we take D to be n alpha, we'll get n to be greater than 1 over alpha epsilon, something like that. This is the most naive lower bound for this problem. So if we take P1 to be Bernoulli half and P2 to be Bernoulli half plus alpha, so we will get the exact lower bound for binary case, right? So, and now the problem is that this bound doesn't have any dependency on K. So we need to find some better coupling for this problem to incur the dependency on K. Okay, so what did we do? We just use some Lee-Ham's two-point method. We construct two hypotheses and a coupling between them with very small expected Hamming distance. Okay, so what is, I will go quickly here. So what did we do? We just designed the following hypothesis testing problem. The first hypothesis is just NIID samples from uniform distribution. And the other one is not only one distribution, it's a mixture of a lot of distributions. And you see the distribution, you can see it as a small perturbation on every position of the uniform distribution. You have some plus, you have some minus, something here. But everyone is alpha away from the uniform distribution. And here you just use a mixture of it. So, and we can bound the coupling distance of uniform to mixture to be something like this one. So because of this lemma, we just take D to be something by this one, and we will get a lower bound of our main theorems. Yes, and I will skip this. Okay, and I will also mention another problem we look at in this paper is a colonies testing problem, also named as two-sample test. In the identity testing problem, we have only one distribution known and one unknown distribution. But here, what we have two unknown distributions. And what is the problem setting is that we just draw NIID samples from P and also from Q. So given these two N samples, we just want to classify whether P and Q are the same or they are far away from each other. Okay, this is the problem of closeness testing. So this is different with the identity testing that we don't know any of the distributions. So it can be seen as a strictly harder problem than the identity testing. So in the literature, the bound for the non-private case is known, and is tight. It should be K to 2 over 3 plus square root K. Depending on which one is large, depending on the number of the parameter, depending on the parameter ranges. So if k is quite large, the first one will dominate. Okay.
So these bounds have some similarity to this bandit versus like non-bandit problems. Is there any relation?
I don't know. So I don't know a lot about the bandit. Yes, bandit problem.
Do you also get those kind of terms, right?
Not 4/3.
Oh, no. But 2/3.
You're saying regret bounds?
Yeah. I don't know. This is so recent, it's in 2014. Really? Nice. So there is...
Getting the right answer for it, yeah.
Yeah, the problem appears when.
There was, I think, an original paper which had like k to the 2/3 from some time ago. This might even be one of the original Bot2 papers, but I think actually getting this trade-off between these two terms is fairly recent.
Yeah.
Nice.
The Bartis paper should be 1980, I remember, as far as I remember. Which is the paper, this problem appears first. Yeah, but the bound is not too old. Okay, so, and we show we can also privatize some non-private estimator to have the following bounds. We have the two items, it should be the maximum of the following two. So, and also, okay, we skip this one because Jenna thinks it's very weird. So let's see, when k is
Well, I think doesn't matter, but yeah.
Just kidding. So I'm just saying, if we don't care about the privacy, we will have exactly the same bound with a non-private case. Okay, and also suppose when k is large, we will have a tight bound for these problems. Why this is tight? Because this is just a bound. The second term is a bound from identity testing, right? And we know this problem is strictly harder than the identity testing problem. So this should also be a lower bound for this problem. So when k is large, we will get a tight lower bound for this problem. Okay, so conclusion for this first work. So what we do is that we establish a general coupling method to prove lower bounds. We also have derived optimal sample complexity. We also give some sample complexity of closeness testing. Okay, I will go over the second work quickly. So in this work, we also consider the differential privacy setting, but we consider another problem, which is the property estimation. Here, the property is a property of some distribution. Suppose we have some P, which is unknown discrete distribution. So, and we want to estimate FP, which is some property of distribution, for example, entropy. It should be the property of the distribution itself. Okay, and alpha is some accuracy level. The input is some IID samples drawn from P. And what we want to do is that we want to output some estimator F hat such that with high probability, the
Constant, yeah.
sorry?
Yeah.
Yeah, the estimator should be close with the real value within accuracy level alpha with high probability, something like 2 or 3. So, and we also want to know the sample complexity for this problem, which is the least number of samples to estimate FP. Okay, is the problem clear? So, and
To answer, I guess, your high probability question, you can always boost to high probability with the usual tricks.
but it's not clear in the private setting.
Even then,
Yeah, it's not clear, but anyway, yeah. Yes. I think since we are running late, I just want to go back once. IID samples. So now FP is just some property of this. Okay, everyone.
Okay, so now what we, we also consider the differentially private property estimation problem. So we require our estimator to satisfy, the first is accuracy, the same accuracy as the previous slide. And the second is the privacy. We also require our estimator must satisfy epsilon differentially privacy. It's also global differential privacy model. Okay, so we consider the following 3 properties. The first one is the Shannon entropy. The second one is the support coverage, which is the expected number of distinct symbols if we draw M samples from P. Okay, so what I want to explain more about it. Suppose we have some unknown distribution and we draw M samples of it. Okay, and you will see, and let X to be the random variable, which indicates the number of the different symbols which appear among the samples. It should be a random variable, right? But here we consider expected number of it. So we should be a fixed value. I will explain more for this one, and I will use this one as a running example. And last, which is the support size, which is the number of symbols with non-zero probability. which is easier to understand. Okay, this is an example. I don't.
Thing is much harder problem, right? Number of symbols with non-zero.
Yes, but the underlying assumption I don't mention is that we assume everyone has probability greater than 1 over k.
K is still the support size.
Yes. No. Yeah. So because if you have something which appears very small probability, you need to see it with a very large size of samples, right?
Yeah.
Which is impossible if you don't have infinite number of samples. Okay, I don't have time for these motivating examples. So, yes. Okay, so
I mean, it's just the second bullet towards what you're saying is just like generalization of coupon collector kind of problem, right? Like
yes. So, when you draw some.
I mean, coupon collector is kind of like the opposite direction. How many times until you definitely see everything, and that takes sort of like k log k.
Right.
This will be.
I see.
Yeah, this should be
If I
connected.
draw only m, then how many you will see? Okay, yeah, it's.
Yeah.
And it's the other way in the sense that you'll be able to save a log k, but maybe I'm spoiling some of this.
So I have a question. What second one is a simple application of McDiarmid inequality?
Sorry?
So isn't it an easy chain of bound argument that because S is Lipschitz, right? Maybe we can
S is
I think I'm wrong.
Okay.
Sorry.
I guess the real goal is, can you do this with fewer than?
Say it. So what you want to say? It follows directly.
From the, I think McDiarmid inequality, because S is a Lipschitz function.
On what? On P? You mean on PX? Is it a Lipschitz function?
So if you have a subset of m examples and you change one of them, the S of m wouldn't. So define the function that I sample m examples, and I look at different distinct values.
Right.
So this is my function. This is a Lipschitz function.
Okay, but the problem, this one only works when you have okay, it only works when m is very small. So, okay, let me put it in this way. Suppose you have some support size k. This one only works when you have a lot of samples larger than k. But if you have only require some very small sample compared with m, this one doesn't work. Yeah, something like that. Yeah, but this is true when you have much more samples. You have any comments?
I guess what you're saying is exactly correct. If you had more than m draws from P,
Right.
you could group it up into sets of size m and just see what the value is, and this will concentrate. But the surprising thing that he'll show is you can do this with far fewer than m draws from P.
Right.
Okay.
Yes. Okay, so let's keep the motivating example. So our main results are the cost of privacy in private property estimation is often negligible. Okay, so the same for all these three problems. I will only talk about the support coverage problems. This is our upper bound. So this upper bound, you can see the first one is tight for the non-private case. It's optimal. And the second one is a bound for the cost of privacy. And we can show that privacy is free unless epsilon to be very, very, very small. So because suppose epsilon to be something like 1 over something like some constant, you will see this will have almost no cost of the privacy. Any problem? And maybe I need to stress this bound only works when the m is very large. M is greater than 1 over alpha epsilon, something like that. So maybe you are curious why this one is strictly larger than this one. It's because we have some assumption that we are in the m is very large setting. Something like that. Okay, so yes. So we just show that the privacy cost is very small here. What we do is just a Laplace mechanism, which I have already covered.
Wait. So I found the bound without even privacy is slightly weird. So you're saying that to estimate the expected number of the support coverage, you actually need m over log m samples.
Yes, you don't need more than m samples.
Because you are only interested in an.
But this one is tied for any parameter region. So you don't need to see exactly m samples, right? Because when you exactly say m samples, or constant number of m samples.
No, but you have error of alpha. Okay, yeah, 1 over alpha.
Yeah. Okay, so what we do is just a Laplace mechanism. We borrow the following non-private estimator from Oli's key, so with some low sensitivity. So what we do is that we bound the sensitivity of this one, and we just add some Laplace noise, and we show the bound in our main theorems. And also we use the coupling lemma, so we already used in the testing problem, so to prove lower bound for this problem. Because this one is strictly harder than the hypothesis testing problem, right? If you want to, for example, if you have the U1 is uniform over this one, and U2 is distributed over n plus 1, so we have one huge mass of about alpha divided by 1 plus alpha, and everyone is the same with this one. So and we can show that the support coverage will differ by alpha m. And if you can estimate this one accurately, you can also distinguish between these two. Okay, I see. So we just use the bound from the hypothesis testing and show a lower bound of the 1 over alpha epsilon. And we also do some experiments. So we just show the real the private estimators and the non-private estimators doesn't differ a lot on the utility. Okay, so also on some real data sets. So conclusion, so our upper bound show that the cost of privacy is often negligible, and we derive some lower bound for these problems. And also we show the effectiveness of it by some synthetic and real data samples. Okay, I think this is all for today. I will skip for so yes, I don't have time to cover it. Any problems? Any questions? Sorry.
So I have one question. So like here, this one sample seems like I'm more interested in seeing that since the privacy almost comes for free, right? Like how many samples I need to change before I actually like have an effect, right?
Also, which problem? Identity testing?
Any of these settings, right? Like, so you're applying strict differential privacy definition where you change only one sample. But suppose I allow to take epsilon fraction of the samples. Do you think many of these things will when will they break, right? I mean, so
for example,
some sensitivity goes up, so you have a good, because oftentimes people always ask this, because this one sample, it seems too strict. Like oftentimes there is a good fraction of the samples coming from the same user. And this may be the set of problems where actually.
But I mean, differential privacy lets you quantify this, right? Like, if you do changing of two things, and you have a 2 epsilon guarantee.
Yeah, but that's what I was saying. But here, when will it break, right? I mean, but I also feel like here you could be able to show some amplification kind of thing. So it's not I
you think you can get better than?
Yes, I don't think naive composition is the right answer for this. Yes.
So I'm thinking. So for example, if we only look at the example of the Bernoulli case, we have some threshold like this one, right? So when you change, suppose n is very large, when you change a constant fraction of it, it will not break your bound.
Exactly. So that's
something like that.
It could be interesting to actually see whether you can show bounds which are which we can bypass even strong compositions.
I see. Yeah.
I mean.
Yeah, I think for a lot of these statistics, it should be pretty easy to analyze because often the privacy is just done by sort of a gap into quantity.
Exactly.
So you can see
and also the non-private things should already be pretty robust in the sense.
Yes, because So suppose you are here, but n is large, you need to change a lot of almost half of it.
Yeah, that's what.
To make it break down.
Right? Exactly. So that. But on the other hand, if I simply invoke strong composition, then it wouldn't give you this strong guarantee. Okay.
Any questions? Yeah.
So are these closeness and identity tests studied for Markov chains as well?
I'm not sure. I think there is some work, but I'm not quite familiar.
Wait, but you're saying
You don't have an example.
Yeah,
There's some works. My advisor, Kostas Daskalakis, has worked some on this, and other people as well. I can link you to some if you're curious.
Yeah, I think.
Are you studying differential privacy?
Yeah. I do differential privacy a lot of these.
cool.
Okay.
So
Thank you.
no questions. Thanks.